All right, so that's not going to move more. So after some algebra, which we're going to do. So basically we have, let's recall it from the previous page, A sub naught equal to basically the same expression here, the F sub naught on top, divided by the same thing over here, K minus M capital omega square plus I C omega. And remember, this is a complex quantity, indicating that there would be a phase, no, a lag in time between the response and between the time of the force and the response. So now using the trigonometric relation, A plus IB times I minus IB, we know this would be equal to x squared plus b squared. So we can kind of do something similar. This would be equal to what? We can rewrite x sub naught as f sub naught factor of k minus m omega square minus ic omega. And the bottom we do k minus m omega square plus ic omega times k minus m lambda square minus ic omega. Okay, so basically what I'm doing is multiply top and bottom with the k minus omega minus ic omega, no? All right, so now I can apply this, and we'll have that x sub naught will be equal to f sub naught, and this will be a square plus b square, so this will be equal to k minus m omega square plus c omega square, and now this will be multiplied times this term, k minus m omega square minus I C omega. Okay, today we have a lot of this type of algebra, so all right, next, recalling from complex algebra, you know that a complex number, you can write it as z bar equal a plus ib, but we can rewrite this complex number by the amplitude times the exponential of I, let's say phi. Okay, you remember this, ask me, okay? But this is just complex numbers. Okay, and similarly, but I'm going to go to the line. Everything is getting very crowded. If you have the z star, what does that mean? This will be a minus ib, and this will just be equal to z star. Sorry, I forgot the star here. Z star e, but this time on minus I phi. Okay, so in this problem, what is the magnitude equal to? You know it's going to be just a squared plus b squared, so it's going to be, this is the magnitude of the frequency. So it will be equal to square root of a plus ib times I minus ib. And this is the square root. Wait, I just put in all the detail. This is the same as doing the z dot z star, basically. All right. And using this relation here, we know that this would just be equal to x squared plus b squared, as I said before. So this is the amplitude. And phi will be the phase. And like the other one would be equal to tangent minus 1, so the inverse tangent of b over a. Okay, I'm doing all this stuff because I told you you don't need a book, so I try to give as much as I can on the classroom. So let's rewrite now this complex quantity here using this notation. All right? So I'm probably going to need to write it somewhere here. Okay, so let us rewrite the below complex term as, so that term that we're trying to rewrite is k minus m omega square minus I c omega. So basically this one over here. All right, so in this equation, this will be A. This is what A, this is our B. So what would be the amplitude? Would be K minus M lambda square plus C omega square, and we take and we need to take the square root. Okay, and now this will be times, I will put it later, times the E minus I phi, where phi will be tangent minus 1 of B, which is minus C omega divided by A, which is K minus M and the square. All right, so this term over here, basically we know that it is the amplitude. Okay. So the expression for x sub naught that we had on the previous page, this one here, will become what? So we had x sub naught equal to f sub naught k minus m omega square plus c omega square. And now we have this new term here that will be k minus m square plus c omega square 1/2 e2 minus I phi. Okay, so we can write this as x sub naught will be equal here to f sub naught k minus m lambda square plus c omega square. And this is 1/2, this is power 1, no? So this really will be to the power minus 1/2, no? So this is, we could take the square root over here. It was just easy to put the minus 1/2 or the 1/2 over there. E of minus I phi. Okay, let me maybe just rewrite it. I think it would be easier with just, instead of putting the square root that makes too many lines, let's just say this will be this. It's the same thing, okay? I'm not changing anything. I just think I might be a little bit more clear. Okay, but to the power 1/2. All right, so now we don't have any more complex quantity, no? This is fully defined. So now what should be the last step? Should be to go and replace into the assumed solution. So finally, substituting x sub naught into the assumed solution. So what was the assumed solution? The assumed solution was x of t will be equal to x sub naught e of I capital omega t. Oh, guys, forgot here. I forgot here from here to here. I forgot this term, e to the minus I phi. Sorry for that. So if we do that, what we have, we're gonna have x of t. The final answer will be equal to k minus m lambda square plus c omega square to the power 1/2 f sub naught. And now here we're gonna have ei. So we have here omega t and here minus I phi. So it will be I omega t minus the change of phase angle. So this is the solution to the force vibration. Okay, so this is basically the response, but like I just said before starting this derivation, I like this notation, but in the textbook, they use more the notation with the damping ratio, okay? So let's just rewrite this solution in function of the damping ratio. All right, so let's say that with some additional algebra, the solution can be rewritten. Okay, so what is that additional algebra? So basically, if we have the term K minus M capital omega square, everything square, plus C omega square. So here now what I'm going to do on the next step is to factor out by M squared. Okay, so what would you get if I factor by M squared? The first term will give you K over M minus omega squared, no? And the second one will give you plus C over M omega everything squared. And I forgot here the square, sorry. The first time. So now, do you maybe recognize what is K over M? K over M is the natural frequency, no? That was defined. You can say omega n squared will be K over M. And also, we derive that C over M, we did that with the free vibration, could be rewritten as in function of the damping ratio, 2 times xc omega sub n. Okay, we did that for the free vibration, okay, that notation. So now basically you see this term here becomes omega n, this term here becomes 2c omega sub n. So that means that over here, this term will become m squared factor of omega n squared minus, so lowercase omega square minus capital omega square plus 2c omega sub n square. All right, and finally, if we factor out, this is a bit not that obvious, but let's factor out by omega n to the fourth. Will give you what? 1 minus capital omega over omega n squared plus 4 c squared capital omega over omega n squared. Okay, so let's say the solution x of t becomes, so I'm not going to write it, we have here this term, this one remain unchanged. This is the term that we just changed the notation, no? The one on the denominator. So let's just replace it by this one over here. So this is going to give us what? X of t. And we need to take the, be careful here because we need to take the square root of this one, no? Yeah. And here we did not take the square root. So that means that what will happen here? We have m omega n squared, no? Okay. So that you are not confused now when I write. To have that x of t is equal. So what did we have? We had x of t will be equal to f. I change a bit the way it's written. So this m, I keep it with this one. And now this term, I just keep it in one term. So will be all this term here would be omega n square of 1 minus omega over omega n square, everything square, plus 4, and just recopying this term now, omega over omega n square. There we go. And this would be the 1/2 times e of I capital omega t minus phi. Or this can be written as x of t equal to f sub naught over m h sub m omega of e, I omega t minus phi, where the hm omega is equal to, oops, I forgot to put a 1 here. Okay, so let me just square everything because it's the same expression. All right, so a lot of algebra, no, so far. Okay, so all this stuff to show you what. So what is that is plotted over here? This is h of m omega, this function, and here we're gonna have in function of the ratio of omega, the force frequency, divided by the natural frequency. Okay, so let's see what I have over here. Okay, so this is the important part, is to realize, so this is very important here. If we haven't here studied before, we kind of look at it to the figure very quick last time, but so now the response x of t, f sub o over m will be a constant, no? Yeah, so the amplitude will depend mostly on this term. Okay, so this is in function of omega over omega n, so this will be your variable. Force frequency is also constant, But let's see what happens if you change now the natural frequency. So let's see over here. If you change this variable, what do you see? Is that if we start from 0, the beginning, the amplitude is 1. And then when the force frequency is more or less, it starts getting closer to the value of the natural frequency, what's happening to the amplitude of the response? Is going to infinity if there is no damping. All right? That phenomenon is what is known as the resonance, which is something you don't want to happen in your structure. Okay? You don't want resonance. So now you see that once you pass this frequency, again, now the amplitude is going to start going down, and the higher you go, actually it goes even smaller. Okay, so now we know what happened at resonance. Let's see what is the effect of the damping into all this stuff. It makes sense. If the damping is 0, this should go to infinity, okay? But what happens if the damping, you start increasing the damping? You see that now the damping is going to decrease the amplitude. All right, and here maybe it's hard to observe. I don't have a ruler, but something that also should happen is that if this is 1, you can see that as the damping increases, the peak kind of moves to the left, no? Decreases. Does that make sense or does that make sense? That makes sense, okay? I'm going to show you now with the equation. Okay, why is that? What does that make sense? I mean, basically it's right over here. As the damping increases, the resonance peak shifts to the left because of the relation. Now the damping frequency, the omega sub n that we had, is not omega sub n anymore, but it's what? It's omega sub n times the square root of 1 minus c squared, no? Yeah? So when c is 0, omega sub d equal omega sub n. But when you start increasing this one, this omega sub d will be smaller than the omega sub n. Does that make sense? Okay, but important thing here to observe is to understand the phenomenon of resonance, and that the damping, the function of the damping is to decrease the amplitude, okay? That shift generally to the left is very small. The important part, the big variable here is the amplitude. So I will put this page with the notes. Not good. All right. Like, I don't know what was the last time I put the recording, but basically now we're just talking that the assumed solution, you assume the solution, but now for the force frequency, the solution is going to have two parts, one an homogeneous part and one a particular. So the homogeneous solution is for the case when the forcing force will be equal to 0. The particular will be when to solve for the value of f of t, that will be this expression. So when this is equal to 0, all right, we derive the solution in, let's see, we derive the solution in the pages, I don't know, have it here. Okay, so I think we had these pages here that give you the response for the underdamped. All right, so we have all these expressions here, summary of results, critically damped, underdamped, and overdamped. So it looks as being from page 41. This was the response. So 41, 40, 39. So we have these ones, critically damped. I think that was the first one. Solution to the free damp system. So it looks like 35 to 41, okay? From pages 35 to 41. where, if you want, I'm just going to summarize it very quick since I have it here in front of me. We had that for the case that delta, so the damping was positive, or the damping ratio is much higher than 1. This was the case for the overdamp, and the response was of the form, I'll put it here, x of t equal to, oops, not a good choice, x of t was equal to C1, C bar 1 exponential of minus C plus C squared minus 1 square root omega and t plus C bar 2 exponential of minus C minus C squared minus 1 square root omega and t. The other case was when this is equal to 0 or C equal to 1, which is the critically damp. In that case, this is the easiest one, x of t. We have the repeated roots was e to minus omega and t, c bar 1 plus c bar 2t. And finally, which is the most common, when the damping ratio is more than 1, is the underdamp, which is the one of interest. In that case, the simplified notation was x of t was equal to exponential of minus omega and t times c bar 1 e of minus I omega dt plus c bar 2 e of positive omega dt. Okay, you had all this stuff in the notes, okay? I just summarize it over here. All right, so the particular solution so sorry for that. If you want, just put over here, if you want, this would be h x of h, x of h, s of h, okay? The particular solution, x of p, is solved by assuming the solution as. So basically, it's the same thing that we did before. So this one is the force frequency, which is this f of t, no? What do we do with the exponential rotation? We assume to be the response in function of the same frequency, okay? So here we're going to do the same thing, but with the trigonometric notation. We're going to assume x of p to be equal to a sub p cosine omega t plus p of p sine capital omega t. So this is our assumed solution. Okay, so our equation has what? X dot, and x double dot, no? So if you want, let's do in detail. So in this case, x dot p will be equal to what? Will be equal to minus a of p omega sine omega t plus p of p omega cosine omega t. And the x double dot of p will be equal to what? Will be equal to minus a sub p omega squared cosine omega t minus b of p omega squared sine capital omega t. So by now you should know the step two. Step two is going to be replace this, substitute this into the equation of motion. Okay? So substituting into equation of motion, which will be m, but instead of x, we say will be x of p plus c x of p. So it will be x equal x of p plus kxp is equal to f of t. I'm not gonna space. Okay, f of t, where f of t was equal to what? A sub naught cosine omega t plus b sub naught sine capital omega t. Do you guys follow? I mean, it's all the time the same thing, no? Once you know the procedure. All right, so that will give us what? We'll have m, let me do one. So this will give you m, x double dot, xp double dot, we say was equal to minus a sub p omega square cosine omega square minus b sub p omega square sine omega t plus c x dot. So x dot is equal to minus ap omega sine omega t plus b of p omega cosine capital omega t and kxp plus k. So now it's just the assumed one. X of p is ap cosine omega t plus b of p sine capital omega t. Okay, and this is equal to a sub naught cosine capital omega t plus b sub naught sine capital omega t. So basically, if you want me to put some detail here, this will be the x double dot p. This is the x dot p. This is the xp. And this term over here is the f of t, okay? In this equation here. All right, so this will be step 2. Maybe I should have put here. Okay, and step 3 is always solve, okay? So over here is again some algebra. So what do you think we're going to do over here? Everything is in function of cosine or sine, no? So we're going to factor by cosine and sine and see what happens, all right? Okay, so rewriting the above equation. We're going to have, okay, we're going to start by the cosine omega t. So this would be minus m a sub p omega square, and put it other terms in function of cosine omega t. Then we'll have plus c, no, the same one, plus c bp omega will be this term, and the last one will be plus k a sub p. And now we need this one on this side, but remember this one is on the right hand side. So we can put it here minus a sub naught cosine omega t. I mean, there's another way to do it. We can leave this one on the other side, but I decided to do it this way. And now the sine omega t term will be equal to what? Minus m b sub p omega square yeah, okay. I'm not going to change it. Nothing will be more clear in another way, but it doesn't matter. So it will be this one. Then we'll have minus c a sub p omega plus k b sub p minus b sub 0 cosine omega t, and everything should be equal to 0. So, okay, what I was trying to say over here is that maybe it would have been better to keep this one, you see this term over here on the right hand side as it is, and then say, which is the same thing, those two expressions will be equal when what? When this term over here, which is in function of cosine omega t, will be equal to a sub naught, no? Or now we could just say that when this term, so this will be equal to 0, when this term is equal to 0 and this term is equal to 0. Do you understand that? Yes? Okay. So the above equation is satisfied if and only if the two equations are equal to 0, so only if minus m a sub p omega square plus c b sub p omega plus k a sub p minus a sub naught equals 0, or when minus m b sub p omega square minus c a of p omega plus k b of p minus b naught equals 0. I know today's a lot of writing, okay? Sorry, but I want to get done with this, okay? And after that, we're just going to use the exponential notation. Okay, so now what we need to do is to solve this system, okay? That system over here. What would be your two unknowns? A of P and B of P, no? Because A sub naught is in function of the forcing frequency, so you assume that everything is known over here. Your known would be A sub P, B sub P, which is your assumed solution. Okay, so solving system for AP and B sub P. You're gonna get A sub P equal to N A sub naught omega N square minus capital omega square minus B naught times C omega divided by N square omega N square minus omega square plus C omega square, and B sub P equal to N B sub naught omega sub N square capital omega square plus A sub naught C omega, and the denominator is the same. Okay, so let's say here the solution x of p is found by substituting A of p and B sub p into the assumed xp solution, which was what? X of p assumed solution, we had, what do we use? A sub p, no? If I remember right, yeah, A sub p cosine omega t plus B sub p sine omega t. Okay, so I'm not going to put those values, okay? I think it's a waste of time. Okay, so the total solution x of t is given by what? X of t is equal to what? X homogeneous of t plus x particular of t. All right, so to finish, we're just going to say that x of h of t gets damped to 0, so x of h of t, let's say, will go to 0, and the total solution comma in most cases is equal to the particular solution. So x of t, let's say, will be x of h of t. This one will be going to 0 plus x of p of t. So at the end, we can say that x of t approximately equal to x of p of t. All right, guys. Let me stop this.